Going to move on to a new section, a section that looks a little bit different from the rest of the unit. This section of the unit is on energy. Does anybody remember the definition from energy, or of energy, I should say, from grade 9 or grade 8 or whatever it was that you learned it the first time? Roger? It's the ability to do work. Yes, it's exactly the exact definition that I have written down there. It's the ability to do work. It doesn't mean that energy is doing work right now. It doesn't mean that it's doing anything. Okay, right now, the remote control for my projector here is in my hand. It's doing nothing right now, but it has energy. It's just stored energy. It's in the form of potential energy. It has the ability to do work later on. Versus if I take this pin and I drop it, it's actually doing work as I drop it. So energy is the ability to do work. It's either doing work right now or it can do work later on if we release that stored energy. Two kinds of energy. You guys remember what they are? One of them we just talked about a second ago. Yeah. One of them is potential energy, yes. Potential energy is stored energy. That's what the pin had before I dropped it. That's what the remote control for the projector had as I was holding it in my hand. It's not energy that's doing something right now. It's energy that might do something later on. Kinetic energy is the other kind, and it's the energy of motion. As I dropped the pin, it began to move. The force of gravity pulled it down, did work on it. Pin began to move. Kinetic energy can always be gotten from potential energy. So potential energy can always be converted to kinetic energy. In other words, energy that has the ability to do something can always become energy that is doing something. Potential can always become kinetic energy. Let's look at some types of potential energy, types of stored energy, objects that have or things that have potential energy in different situations. What's one of the kinds? The example that I just gave you, right? The remote control has what kind of potential energy? What is the energy stored, the stored energy in this remote control due to? If I drop it, it falls, right? So if I drop it, it gains kinetic energy. Why does it gain kinetic energy when I drop it? What causes it to gain kinetic energy? Yep. Sorry? Yeah, forces. It's always forces, right? But what force is it? It's gravity. So we're going to call that gravitational potential energy. One of the kinds of potential energy, one of the kinds of stored energy that we have is gravitational. But we can store energy due to a number of other things as well. What's one other way that we can store energy? Remember, stored energy, always energy that can be converted to kinetic ultimately. What's one of the other ways that we can store it here? Daily. Yeah, no, that's good. You can store it in a battery. That would be electrical potential energy. And we're not going to talk much about electrical potential energy in Physics 20, other than that it is a kind of potential energy. Physics 30 will talk a lot more about electrical potential energy. Bottom line is, you put a battery in your toy car, what happens to the toy car? It starts moving, right? So that potential energy, the energy must have been stored somewhere. The energy was stored in the battery, which caused the car to move. In other words, the potential that was stored in the battery was converted to kinetic. Rucker, what's another one? Chemical potential energy, which is the energy stored, obviously, in chemicals that can be converted to kinetic energy as well, ultimately. How many people take biology here? You guys know a lot more about it than I do then, about this particular aspect of it. Okay? When we eat, ultimately, that's what allows us to move, right? We get our energy from eating. It's stored inside our body as glucose, or what is that ATP thing? Isn't it stored in ATP or as ATP or something? I don't know. What is that? How does that work exactly? I don't know. It doesn't matter. I don't know a whole lot about biology, but I do know that the energy is in our body, stored ultimately as chemical potential energy, right? And when we need to move, we can liberate that chemical potential energy and convert that chemical potential energy into kinetic energy. So again, this energy can be converted to kinetic energy, energy of motion. Give me something else. You don't necessarily think of this always as potential energy or even energy at all sometimes, but what about nuclear energy? Not the context necessarily of a nuclear bomb, although it could be, but it could also be in the context of a nuclear power plant, or it could even be in the context of just the energy stored in a nucleus. Okay, not necessarily doing anything right now. Okay, nuclear energy, ultimately in the case of a power plant, generates heat. Okay, heat causes steam, causes water to boil, causes steam to rise, causes a turbine to turn and generate electricity. So ultimately, you've got this energy that's stored in the nucleus of an atom that's causing steam to rise and causing a turbine to turn. So ultimately, you've got potential energy that is, again, being converted to kinetic energy. Yep. Be careful with that one. Rutgers says thermal. Thermal would actually be kinetic energy. How do we define thermal energy? Yeah. It's the vibration of particles within something, right? If it's a vibration of particles, those particles are moving, right? So that would be kinetic energy. Rutgers, does that make sense? Yeah. Like an applied force. Okay, well, you got to be careful with that because that's not energy, right? That's a force. Okay, now if you want to take that to a fundamental level, though, when you push on something, obviously you have to be imparting energy to that thing to cause it to move, right? So where does that energy stored? If the object isn't moving right now and you're pushing it to cause it to move, where is that energy stored? It's in our bodies, right? It's stored as chemical potential in our bodies. So when you push something and cause it to move, yeah, there's stored energy, but it's not stored energy in the object itself. It's stored energy in your body, stored as chemical potential, just as it is when we want to walk. It's stored as chemical potential. Kinetic energy, we don't usually differentiate between different kinds of of kinetic energy. And the reason is because kinetic energy is always energy of motion. Essentially, anything that's moving has kinetic energy. There's there's a couple of types of potential energy that we're going to talk about in a little bit more detail. The first one that we're going to talk about literally today in detail is gravitational potential energy. And then one that we're going to talk about a little bit later on, this isn't even written down here actually, we're going to call it spring or elastic potential energy. That's the energy stored in an elastic or a spring that's stretched or compressed. The two that we're going to focus on today are kinetic energy and gravitational potential energy. Now, kinetic energy, if it's dependent upon motion, then it's dependent upon speed. But it's also dependent upon something else as well. Tell me, an object that's moving has more kinetic energy clearly if it's moving faster. A car traveling down the road at 100 kilometers per hour has more kinetic energy than a car traveling down the road at 50 kilometers per hour. What else makes the kinetic energy greater? Yes. If a car traveling down the road at 100 kilometers per hour is compared to a semi-truck traveling down the road at 100, which has more kinetic energy? Be the semi-truck, right? So it's dependent upon mass and it's dependent upon speed. The equation that we use for kinetic energy, you've seen this before, is 1/2 times m times, anybody remember here? 1/2 m times v squared. What does m stand for? Mass. What units do we use for mass? Kilograms, right? What does v stand for? No. V does not stand for velocity. What does it stand for? Good. V stands for speed. It's not a vector. Kinetic energy is a scalar. So V has got to be a scalar as well. That's going to be speed. And the units for the speed here are always going to be meters per second. This is the kinetic energy. You guys remember the units for kinetic energy or any other unit of it? Any other energy for that matter besides kinetic? What is it, Brentley? Joules, yes. And we usually just abbreviate a joule by a capital J. We already know that mass is a scalar, right? Speed is a scalar. And kinetic energy, in fact, any kind of energy, not just kinetic energy, is also a scalar. Now, gravitational potential energy. Again, we'll talk about spring or elastic potential energy another time. Gravitational potential energy, the energy stored in an object due to its height above the ground. The potential energy of this pen has a certain value right now. It has a different value right now. It's a greater value right now because it has more potential to fall now than it did down here. Right? More height, more potential to fall. In other words, more ability to do work when it's up high than when it's down low. If you drop something from up high, it moves faster. It ends up moving faster by the time it reaches the ground. If it's moving faster, it has more ability to do work. Therefore, it's a higher value. The equation for gravitational potential energy, we're going to say is EP is equal to, it's dependent upon height. It's also dependent upon gravity, obviously. If you're on the moon and you drop this pen, it's not going to be moving as fast when it hits the ground. Therefore, it has less ability to do work. It's dependent upon gravity and height. What else? Yep, Josh? Mass, good. Now, that doesn't mean the heavier it is, it's going to be moving faster when it hits the ground. It's not. But it still has more ability to do work when it hits the ground. Okay, if I drop the pen from 1 meter versus a half a meter, and I drop it on some fragile piece of glass, it has more ability to break it from 1 meter than it does from a half a meter. If I drop a heavy pen versus a light pen, it's not moving any faster, but it still has more ability to do damage to that glass when it's heavier than when it's lighter. So it's dependent upon mass, it's dependent upon gravity, and it's dependent upon height. Okay, M again is going to stand for mass, and the units are going to be kilograms. What's G? 9.81. Why am I making that positive? Why am I dropping the negative sign there? Travis? Right, EP is a scalar, and therefore I don't want any signs coming out of it, right? I always want a positive value. H stands for the height, and the units for the height are going to be meters. What are the units for EP? You guys know this, right? Jace, what are the units for EP? Joules, yes. And it's going to be a vector or a scalar. Good. Any kind of energy is a scalar, right? Not just kinetic, not just gravitational potential. Any kind of energy is a scalar. Yeah. That's correct, yes. As opposed to other kinds of potential, is that your question? Okay, yes, you're right. It only accounts for gravitational potential energy. So for instance, and I mean, we won't do a problem like this because chemical potential energy is outside of the realm of physics, right? That would either be a chemistry thing or a biology thing. But strictly speaking, objects can have chemical potential energy, so we got to know that. If I'm standing on the top of a ledge and I want to jump off that ledge for whatever reason, I've got gravitational potential energy that I can find by multiplying mgh. But I've also got chemical potential energy that's stored inside my body that I'm not accounting for by mgh, right? That only accounts for the energy that's due to the height, not that's due to what I ate this morning. Okay, let's say you and I weigh exactly the same amount. Okay, we're both standing on the ledge. I ate breakfast, you didn't eat breakfast. Well, I've got more potential energy than you have, but not more gravitational potential energy than you have. Okay. Is that good? Let's go straight to an example here. It's 6.5 on 303. It says, on a highway, a car of mass 1,200 kilograms traveling at 20 has a kinetic energy equal to a loaded van of 4.8 times 10 to the 3. What's the speed of the car? We're starting off with kind of a tough question, actually. A bit of a tricky question to start off this section with. We've got two masses here. Two objects, a car and this van. Let's call this M1, that's the mass of the car. Let's call this M2, that's the mass of the van. Let's call this V1, that's the velocity, the speed of the car, I should say. We don't know what V2 is. That's what we're trying to find. the speed of the van. Anybody have an idea? First of all, are we dealing with potential or kinetic energy here? Potential or kinetic energy here? Kinetic energy, how do we know this is kinetic energy versus potential? What's the difference? Kinetic energy is energy of motion. Potential is stored energy. Okay, energy of motion, energy that's doing something, versus stored energy, energy that might do something later on. Is this doing something, or might it do something later on? Is this kinetic energy or potential energy? Bailey? This is kinetic energy, right? So our base equation that we use here is Ek is equal to 1/2 mv squared. But my problem is, I want to find the speed of the van. I want to find V2, but I don't know what Ek2 is. I don't know what the kinetic energy of object number 2 is. So what do you want to do? Yeah. Yes. It says the kinetic energy of the car is equal to the kinetic energy of the loaded van. So let's get the value of Ek1. Let's say it's 1/2 mv squared. It's 1/2 of 1200 times 20 squared. 20 squared is 400. 400 times 600 is 240,000 joules. So the car has 240,000 joules of energy, of kinetic energy that is. Well, so does the van, because we're told it's equal. How do we rearrange this to solve for V, though? What do we got to get rid of first? This is almost the worst part of this question, is rearranging it to solve for V. What do we get rid of first there? Yeah? The 1/2, yeah? We can also get rid of the M2 at the same time if we want to. How do we get rid of the half? We could divide it by a half, or we could actually multiply it by 2 would be the same thing, right? So we could say Ek divided by a half, m is equal to V2 squared, or we could have said 2Ek over m is equal to V2 squared. It's exactly the same thing, right? This one looks a little bit nicer, but it's no better. We divided because it was multiplied, right, by the V squared. How do we get rid of the square now? This is the easy part of it now, right? Square root it. So let's do that. Hey, let's say Ek, we just figured it out. It's 240,000 joules divided by a half times the mass of the truck, or the van, I should say, 4.8 times 10 to the 3. And we square root that. Let's pull this up on our calculator just to make sure we're all doing it right here. Let's say 240,000. Let's divide that by, use some brackets here, 0.5 times 4.8 times 10 to the 3. We get a number here. The answer is 100. Is that right? Is that right? Final answer? A lot of you will put that as your final answer. A lot of you will stop right there. This is a very common mistake, but this isn't our final answer. What do we got to do to it? Brendan, what do we got to do to it to make it a final answer? No, even before that. Hayden? Yeah, we got to square root it. So it's the square root of 100, which ends up being 10 meters per second. Now, a question for you, more of an understanding question versus a math question. Why did we get a number that was smaller? Why is this truck or this van have a smaller speed than the speed of this car? We're told the kinetic energy is the same. Shouldn't the speed be the same? Hayden? It weighs more, right? If it's got the same kinetic energy and it's got a bigger mass, then it's going to have a smaller speed. Make sense? All right, I'll give you a chance to finish writing that. All right, let's take a look at these 3 quick questions, please, individually, and then we'll take a look at them as a group. All right, we're going to take a look at question number 2 and question number 3 here. 2 says a car traveling at 80 kilometers per hour on a highway has a kinetic energy of 4.2 times 10 to the 5. What's the mass of the car? In theory, this is not a hard question at all because it's just a straight EK is equal to 1 FMV squared. We've got to solve for mass. The trick, though, is first of all, rearranging it to solve for mass. Okay, and second of all, recognizing that the speed can't be in kilometers per hour, rather it's got to be meters per second. So a pretty straightforward question turns into a little bit of a tricky question here. Let's first convert that 80 kilometers per hour to meters per second. You get 80 kilometers per hour. That ends up being the same as 80,000 meters per hour. All right, we're just converting kilometers to meters first. It's been a while since we've had to do that conversion. 80,000 meters per hour. Now let's convert hours to seconds. How many seconds in an hour? 3,600. So it's going to be 80,000 meters divided by 3,600 seconds, which I believe works out to be 22.222 meters per second. So we've got the speed in kilometers per hour. That's good. Now we're going to have to take that equation. Let's write down the rest of our givens actually first. EK is equal to 4.2 times 10 to the 5 joules. And we're solving for mass here. Let's take the equation, rearrange it now. EK is equal to 1/2 mv squared. And what are we solving for? Mass. We can either take the 1/2 over by dividing, or we can take the 2 over by multiplying. Okay, usually I do it by dividing with you guys, but I'm going to do it the other way this time. Okay, it's the same as mv squared over 2, so take the 2 out by multiplying, or again the 1/2 down by dividing. Now I got to get rid of the v squared. Take that over by, it's multiplied by m, so take it over by dividing. We get 2ek over over v squared equals m. Do I have to square root that? For whatever reason, this is where people make a mistake on this too. People see that v squared and automatically think, okay, I got to square root. Why would you have to square root this? Is m squared? If m was squared, then you'd have to square root. If you're solving for v, you'd have to square root. But since you're solving for m, and it's m already in the base equation, we're done. We don't need to square root that. So we plug our numbers in there. We do our thing here, and we should get that value of 1.7 times 10 to the 3. It's a car. We get a number that's 1,700 kilograms. Is that a reasonable number? Yeah, probably. Okay, cars are usually in that 1,200 kilogram to 2,500 kilogram range, so it seems reasonable. Now, 3 is that other one that is a little bit tricky here. Okay, it doesn't have to be, but there is one thing that can lead to a mistake here for sure. We've got a mass here of 65.0 kilograms. We've got a VI of 1.75 meters per second, and we've got a VF of 4.2 meters per second. We want to find not the kinetic energy per se, but we want to find the increase in the kinetic energy, how much it goes up by. Now, my guess is that this is what some of you try to do. If EK is equal to 1/2 mv squared, then delta EK would be the same as 1/2 times m times delta v squared, right? 1/2 times the mass of 65 kilograms times 4.2 minus 1.75 gives me, what is that, 2.45? 2.45 meters per second. Square that. We get a number that is wrong. That's the wrong answer. So how do we actually do it then? Well, let's get EKI. It's 1/2 mvi squared. VI is 1.75. What do we get for VI there? Does anybody have that? $99.53 joules. Let's get EKF. The final speed is 4.2. What do we end up getting for that, for EKF? 573.3. Now we want to find delta EK. We're going to subtract 573. 573.3, thank you. So delta EK is going to be the difference between those. Just subtract them, we end up getting 474 joules, which this time is the correct answer. Why didn't it work out that way? Why didn't it work out to subtract the speeds and then go 1/2 m times the change in the speed squared? Josh? No, it's not because it's accelerating. No. It is accelerating, right? But that's not the reason why that didn't work out. Yeah? No. No, not because we're assuming different speeds. If it's changing speed, then of course it has to be assuming different speeds, right? Because we're squaring it, yes. Okay, if it was the mass that changed, we'd get away with doing that. But if it's speed that changes, we can't get away with subtracting the speed and then putting it in because it's squared. Okay? If in doubt, just never do that. If in doubt, just do it the way we did the second time, because you're always going to get it right that way. All right? How many people, just out of curiosity, got question number 3 correct? Good, good. How many people got it right the first time, the first try, as opposed to doing it one way, getting an answer, and saying, oh, I got it wrong, I better try again? Okay, good. Okay, we defined gravitational potential energy already. We're just writing down a little bit for it here now. It is the energy stored in an object due to its height above something. Usually it's height above the ground. The gravitational potential energy is relative to something. In other words, say it's usually relative to the ground, but it can be relative to something else. For instance, this pen, the board marker right now. The gravitational potential energy of this board marker relative to the ground is a certain value because it has a potential to fall to the ground. It has a certain height above the ground, therefore potential to fall to the ground. How much potential does this pen have to fall to my hand? None. Why? Because it's already in my hand. So the potential energy relative to the ground is something. The potential energy relative to my hand is nothing because it has no ability to fall to the place where it already is. In other words, gravitational potential energy can be different numbers depending upon where you define your base point to be, relative to the ground, relative to the desk, relative to your hand. And of course, the larger the height above that point, whether it's the ground or your hand, the more potential energy the object has. The more ability it has to do work, because the more ability it has to gain speed as it falls. Again, you've already written this part of it down, but again, the equation for potential energy is mgh. Just remember that that h is that number that's measured relative to something, relative to the ground, relative to your hand, relative to the desk. Usually the ground. Okay? All right, let's take a look at this one now, 6.3 on 298. It says, figure 6.14 shows a toy car track set up on a tabletop. What is the gravitational potential energy of the car, which has a mass of 0.0250 kilograms, relative to the floor? Then we want to find the change in potential energy of the car when it arrives to the bottom of the hill. Well, for question A, we know the mass is 0.0250 kilograms. And let's say the height is what? What height are we going to use here? We're going to use the 2.15 meters or the 0.950 meters? The change in, the gravitational potential energy relative to the floor. What's the height above the floor? What's the height of this toy car above the floor? 2.15 meters. So we got two different numbers there for the height, but this is the one we're going to use. EP is equal to mgh. Pretty straightforward question, I think. 0.0250 times 9.81 times 2.15. Let's see what we get there. 0.45 newtons. Let's go with a few more digits here. 0.45. 3467. And it's not newtons, is it? Joules, yes. So we're gonna round that to 3 digits. Get 0.453 joules. So there's the potential energy relative to the floor. Hey, what if I was asked to find the potential energy relative to the tabletop? Is there a mistake there? What is it? 0.45. Oh, 0.527. Okay, thank you. What if I was asked to find the potential energy relative to the tabletop? How would I have done that? Subtract what? Yes. Yeah, subtract the height underneath the table from the total height that we had there. What are you going to get there? 1.2 or something like that meters. So that would be my height above the tabletop, and that's the number that I would have plugged in. Now, question B says, what's the change in gravitational potential energy of the car when it arrives to the bottom of the hill? Well, we're looking for delta EP. We can say, let's get EPF. The final potential energy would be mgh times, or mass times gravity times the height of 0.950. Final height of 0.950. What do we get there for the final potential? 0.233. Is that my final answer? That's my potential energy relative to the ground. What am I looking for here? Subtract them, right? The change. Let's say final minus initial 0.233 joules minus 0.527 joules. What am I going to get there? Negative 0.297? Negative 0.294? Hey, why is it negative? That's my final answer. Why is it negative? I've gone down that much? Yeah. 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 Really? It's when it's the bottom. A negative energy doesn't mean for us down because energy is a scalar, not a vector. So negative doesn't mean direction. Rather, it means that go ahead. Yeah, it means we've lost the energy. A positive delta E is a gain. A negative delta E is a loss. Now, one more quick little thing before I set you free on a couple of questions here. We could have solved this slightly differently. We could have said EP is equal to M times G times delta H. And when we would have done that, we would have gotten negative 0.294. Delta H would have been 0.950 minus 2.15. How come I could subtract the heights there in this question, but not the speeds in the last question? When we subtract the speeds, we get the wrong answer. When we subtract the heights, we get the right answer. Why? Why? Go ahead. Right. The heights are not squared. The speeds are. So as long as it's a linear thing, mgh as opposed to 1 fmv squared, it's okay to do that subtraction there. Okay, but in the end, it doesn't really matter. Okay, if you want to just find the final initial energies, just like you did in the last question, then do that. Works too. Okay? Give you a chance to copy that out if you haven't already. All right, let's try these three, please, on 498. 298, page 298. I want to take a look at question number 2 here, first of all. Number 2 says, a roller coaster trolley begins its journey 5.25 meters above the ground. Its motor tows it to the top of the first hill. It gains this much energy. The mass is 875. How far to the top of the hill is the top of the hill above the ground? So we've got an initial height here. It's 5.25 meters. We're looking for a final height. That's how high is it off the ground at the top of the hill. We've got a change in energy. It's not an E. It's a delta E. Okay, it's what it's gained. 4.2 times 10 to the 5 joules. And we've got a mass here of 875. Now, the way that I did this question, there's a couple ways to go about this one, but the way that I did it is to say, look, we know what delta E is. We can find EI pretty easily. EKI, or EPI, I should say, is mghi. That's going to be 875 times 9.1 times the initial height of 5.75. Does anybody have that value? Sorry, that was 5.25. 45064. 0.6875, thank you. Now that's my initial potential. If my change in potential is 4.2 times 10 to the 5, let's find my final potential. It's going to be EF minus EI. So in other words, EF becomes equal to delta E plus EI, the change plus the initial. So it's going to be 4.2 times 10 to the 5 plus 45064.69. Okay, we get a number for that for EF. Now that we've got a number for the final potential energy, the question is easy now. At this point, all we have to do is say EF is equal to mg HF, and we solve for HF. Now, the other way to do it is walking around. Cassidy had done it a little bit differently. She said, I think she said, Cassidy, what did you do exactly? I can't remember. Oh, you calculated the height change, right? Yeah, so Cassidy said delta E is equal to mg times delta H. She had this, she had this, she had this, and she found this. She was allowed to do that because it wasn't squared, right? So she found delta H, and then you added 5.25 to the change in height. So that method might actually be a little bit quicker, a little bit shorter. I wouldn't say one's better, but that might be a little bit quicker and shorter. Real quickly, guys, number three here, we're not going to go through this question, but I want to ask you real quickly what relevance that 35 degrees has here. Yeah, in the end, you need a height, right? Okay, you're not going to plug in the 35 degrees into mgh. You're going to just use the 35 degrees along with some trigonometry to find the height. Once you have the height, you treat it the same way as any other question, right? All right, so finish, please, those three questions. In addition, once you finish those, your homework is check and reflect question, page 305, questions 7 and 9, okay?